So moving forward, now we can talk a little bit about matrix decompositions and how they're used in our research and why they're useful. So I kind of wanted to give some intuition about why we do this. So what is a decomposition, first of all? Well, it's essentially going to be a factorization. So if I start with some matrix M, and I want to decompose it into smaller, more manageable parts. So, or maybe not necessarily smaller, but I want to decompose it into more manageable pieces. I want to kind of break it up into these parts that I'm going to operate on now. And so usually what I'm going to do is I'm going to decompose my original matrix into a set of more vectors or directions and scalars. Why is this useful for us? Well, now we can store things. Maybe we're going to reduce the storage size of our original matrix. Our decomposition can actually be a bit smaller than our original matrix in some cases. So this also motivates the idea of dimensionality reduction, where now we're going to have smaller matrices and data exploration. So if I look at my matrix in terms of these smaller components or these smaller dimensions, can I understand something that's going on a little bit better in my matrix? And can I visualize things a bit better? So inherently, these decomposition methods are going to assume that all the information you care about in your matrix is there. So I don't need to look at something externally. I can decompose my matrix and probably find the information that I care about. Now, how is this usually done? Well, usually we're gonna do some sort of decomposition that's gonna, again, give us some sort of vectors or scalars. But how do I think about this? How do I think now I have these extra directions that I didn't have before, and I have these extra scalars? Why are these what's so interesting about my decomposition? What do they mean? Well, let's think about this. We're actually going to be doing something that's analogous to finding the roots of a polynomial function. So like a polynomial function, we can find essentially the roots of a matrix, or we can understand the characteristics or traits of our matrix via this decomposition. So let's say I had a collection of points. Now, from this collection of points, I can kind of think or extrapolate what my function looks like, my polynomial function, or linear function. Maybe it is a linear function. Looking at it the way it is now, it could just be a straight line. And I don't really know what it is, but these are the points I have. Well, let's say it did have the function, and I could actually find its roots. Well, now I can see it most likely is a polynomial function. It has these points, it has these roots, so it must be touching the 0 line and also these points. And it's not really a straight line I can draw through it. Okay, I'm learning a little bit more about my function via these roots. And now I can start to build a little more. Okay, what about my minimum and maximum? Do I have a better idea what my function is going to look like? Yeah, I'm gaining a bit of information here. I can probably start to think about what my function is going to look like. Lastly, if I find these other points that are going to tell me about the curvature, well, it's becoming pretty clear what my function is going to look like. And I don't actually need to use the entire function. So I haven't plotted every single point on this function, but right now you probably have a pretty clear idea of what's going on in your function. So again, now I can fill in the lines and see, well, yep, this is pretty clear. We've done a really good job of capturing this function just using its critical points and roots. And so I don't actually need the whole function, I just need these really important points. Now the same logic is what's going to apply to a matrix decomposition. I don't actually need all directions in my matrix. Maybe I just need a small subset that are going to tell me about some interesting features or the way my matrix looks. Now, how are we going to do this? Well, there's going to be a few different ways of getting these important parts of a matrix. But let's think about this again in our analogy of a polynomial. So let's say I had some polynomial and I wanted to learn about its roots. Well, fail-safe, I can just use the quadratic formula. And that's going to tell me some idea about my roots. And no matter what my polynomial is, my second-degree polynomial is, I can tell you what these roots are fairly easily using this formula. In a more easy scenario, I have what's called a perfect square. And so here I can just tell you my roots are going to be plus or minus c. So I can just take the square root of 9 and I'll get plus or minus 3 as my roots. Yeah, so to reiterate, basically what I want to do is I want to find the roots, and with a quadratic formula I can find the roots on any second degree polynomials fairly easy with this formula. But in a more easy situation, I'm going to have a perfect square. And what I can do with the perfect square is I know my roots are just going to be equal to plus or minus c, and in this case 9. So I'm going to get plus or minus 3 as my roots. This is a little bit easier, and I don't really need to use the quadratic formula here because, well, I have this very easy form of solution. But if I wanted to, I could still use the quadratic formula and arrive at the same thing. But I can't necessarily do the same perfect square strategy for any other second-degree polynomial. Now, we're going to switch over to vectors, or in matrices. And now, instead of finding roots, I'm going to be finding these interesting axes, or directions, or components. These are all going to be referred to very similarly in research. And now I'm looking for these axes and these directions rather than looking for points. So how does this make sense? Well, before, let's say we had the quadratic formula and we can find the roots or decomposition of any second-degree polynomial. Well, now I can do the same for any matrix. Any matrix can be a rectangle, square, but I can use a decomposition like the quadratic formula, and I can find a decomposition on any matrix. Well, in a more strict scenario is I'm going to have a square matrix, and I can do another decomposition that is going to provide me some different roots or a different way at arriving to these roots. But as we'll see, is that we can do what's called the SVD, or the singular value decomposition, or the eigen decomposition. Now, what's important here is we can do the SVD on, again, any matrix, and it's going to work for any matrix at all, just like our quadratic formula worked for any second-degree polynomial. Our eigen decomposition, on the other hand, is going to be unique, and it's only going to work on square matrices. So, like we had the perfect square here, and we had a certain solution, and for the perfect square, we could find our roots using this quadratic function. The same idea with the eigen decomposition. We could perform the SVD on this perfect square matrix, or we could just perform the eigen decomposition. And so one way to kind of remember this, well, a square is a rectangle, but a rectangle is not a square. So I can perform the SVD on any matrix, any rectangle, and the square is included, but I can't necessarily perform the eigen decomposition on a rectangular matrix. And so what we've covered here is the idea that these axes and components, they're just important parts of our matrix. So like roots in a polynomial, where we got a better idea of what our function is looking like or how it's behaving, these axes and components are going to tell us something interesting about our matrix and what we care about, the interesting directions in our matrix. And the way at which we can arrive to these components, or scalars that we're interested in, is going to be using the SVD or the eigen decomposition. And I want to, again, thank UCLA Computational Medicine for the opportunity.